I mean, is there something you want to talk about? This will be a little mind-bending, but keep in mind this is not on the crystal. We want to start talking about a very important result called Lagrange error, the Lagrange error bound. It's also called Taylor's theorem. So let's start with e to the negative 2x, centered at 0. We'll use the fourth order Taylor polynomial, and we'll approximate the value at 0.2. The emphasis right now is not coming up on with the series. Hopefully you've just seen even the very last quiz practice problem we just did on the worksheet how to come up with that series expansion. So I'll rush through that quickly here, and then we'll plug in 0.2 into our series, and also in e to the negative 2x, and see how they compare. Just like on the quiz practice, we did that too. Calculate the error, the difference between the two. So you know, feel free to race ahead of me on this. So e to the negative 2x is what we're comparing this to. We'll come up with what does it say? The fourth order Taylor polynomial. So I don't know, maybe we call it T4 or something. P4 for the fourth order Taylor polynomial. So it'll be 1, right? Plus, do we know the power series for e to the x? Plus x normally, except now we have like a negative 2x instead. We'll simplify later. Plus negative 2x squared over 2 factorial plus negative 2x cubed over 3 factorial plus negative 2x to the fourth over 4 factorial. And actually, if you don't even want to simplify, that's fine, because the point of this is not to come up with that series, it's to actually plug this in. So feel free to simplify, but in the end, please plug in 0.2 to this, and plug 0.2 into this, and compare. Compare the results here is the thing we're doing. Feel free to simplify, but let me, here, I'll just check on my calculator. We'll all do it for fun. Okay. Yeah, and hopefully this will be a good confirmation that we're not crazy and that this is producing for us reasonable results, right? Hopefully. So over here we get 0.67032. I'm gonna just store that value temporarily in case I need it, because I'm gonna subtract these two in a minute. I just want to hold on to that. And over here, I guess, I don't know, what do you want to do here? Do you want to just type it in with a 0.2 everywhere in x's, or do you want to plug it into y1? You can do whatever you like. I might plug it into y1 and then. So if you want to simplify, you can, but you don't need to. All right, so I'm getting, for this, someone can check me on this, but exactly 0.6704. Can someone check me on that? Okay. So if we subtract the previous, so I'm getting an error on the order. Well, of course, it only disagrees in the fourth decimal place. So, but the error between these. Call this f of x, I guess, is equal to 0.1234795 approximately. A very small error though. But of course, we expect that because we're using the fourth order Taylor polynomial, which is good. And we're estimating something very close, so we kind of expect the answer. We'd be surprised if the answer was really far off, given the fact that we're using the fourth order Taylor polynomial, which is not a bad approximation, and that we're not that far away from the center of our expansion. So that's not a huge surprise. Okay. So here's the Taylor theorem with remainder. I'm sorry that this is not like on a note sheet for you or something. There's a lot to swallow here, but let me just point out so that it's helpful as you're writing this down quickly. That there's actually a lot here that should be completely familiar. In fact, the whole first part of this is just our Taylor expansion with the coefficient that we love there, the nth derivative evaluated to a over n factorial, right? That's not a huge surprise. All the way up to the nth term, and the thing we're focusing on today is like the leftover part, right? The remainder that provides for us the difference between what the actual value of the function is and the function. So that's why this Rn of x is at the very end here. Just want to make sure you're clear. A lot of times at the end of the series, we still have like a plus dot dot dot, right? And here, this is a finite series, so we're using kind of the nth order Taylor polynomial, but then we're adding the remainder. So for the fourth order Taylor polynomial, we'll call the remainder R4 of x. And the remainder is the function we were just using, the calculation we were just making a second ago. It's like the part that fixes our estimation, right? That corrects it and makes it not approximately anymore, but equal to the function. So I want to make sure we're careful as we're thinking about notation. This equals here is not meant, it's not an approximately equal to. This is an equals here. So we actually get the value of the function. If we take and of course this is maybe not a huge shocker, of course we get the value of the function. If we take the approximation and add the thing that fixes the approximation, of course we get the actual value of the function. This is the approximation that we've been using, even even just on the last slide. And then this is the thing that fixes our approximation to achieve equality, Now, here's the big, so that's not a huge shocker. Of course, like, if you add the thing that fixes it, then it fixes it. Like, of course, that's like almost tautological. The thing that's a big surprise is what this R of n can be said to be. And that's this down here. This is called the Lagrange form of the remainder. And you'll notice, I think the first thing to notice, because you'll be thinking, like, how do I remember this not nastiness? Is in some sense, it's almost exactly like the next term if you were to go one more term. If you're estimating using the fourth order Taylor polynomial, the form of the remainder is the next term, the fifth order term, with one very small difference, and that's that we're evaluating it at not the center, A, but at some constant C. And that C, we can guarantee, is some value in the interval where we're estimating, somewhere in between x and a, somewhere wherever we want to be. But notice everything else is just n plus 1 factorial. N plus 1 is the power. It's the n plus first derivative. It's basically the next term, except not evaluated at the center, but at some value c. Now, the existence of this c is reminiscent. The fact that we're not like we're holding out on you, that we're not sure what c value to plug in, but we know that one always exists. There is some number that always exists, such that this is perfect. This is an equality, but this is correct. That produces a remainder that fixes this. Should sound a little familiar. When was the last time we made some claim about the existence of some c value? Huh? Well, I'm thinking of a little c, that there exists some c. Yeah, the mean value theorem. And in fact, you guys, the thing I've just put on the board, as terrible as it looks, is like the super mean value theorem. If you, in fact, if you, I don't have, yeah, do I have this up here? Yeah, there we go. This should remind you of the mean value theorem, and we can be very specific about this. The mean value theorem is a very specific case of this. Like you might be thinking, really? Is it really true that if, say we just stop at the linear approximation, that is, say we just stop here, or the constant approximation, is this really true that f of x is equal to f of a, the center? And the answer is, yeah, with an error correction. And what's the error? Well, we've just said it's the next term, it's the form of the next term, evaluated not at a, but at c. So this is the very, very simplest case of this result. And that, my friends, is the mean value theorem. Do you see it? We don't often write it that way, maybe. Let's write it the way we normally write it. F of x minus f of a over x minus a is equal to f prime of c, right? Isn't that the mean value theorem? So I'm just saying, for the very, very, very simplest case of this theorem, we have the mean value theorem, right? But we're saying that this generalizes, the mean value theorem generalizes for, we can take this, for any estimate, we can fix it, right? Just like in the mean value theorem, we kind of can guarantee that there exists a slope somewhere that is exactly equal to the average, to the average rate of change. So, this is an existence theorem. Most often we will not ask you to find C. But it's important to note that C has limits over, like, this expression still has limits over what this expression can even be. Let's say C can be anything. How bad could this error still be? And that's really where we want to focus this conversation. And when we were studying the mean value theorem, we often made you find that C value, like makes this true. That won't really be the focus of this unit, even though that would be completely possible to do. Maybe we'll have to go through that and show you how that can be done. Right, Ashley?
Yep.
So this comes from the previous slide then, right? So how bad could the error be? Well, the error we just saw, the error, or the remainder, is of this form. Did you see that? Right? It's the next term that we didn't use, the form of that term. So that's why there's an n plus 1 here and n plus 1 here. These should all look familiar. I've replaced, though, the numerator, the n plus first derivative, evaluated at c. I've replaced that with a capital M here. And up here, I'll just tell you what we mean by capital M is we mean the very biggest value that the n plus first derivative could have on the interval of interest. There's a lot to keep track of here, but do you see why so what we're saying is, who cares what C is? How big could the error even be? So let's just maximize it. Let's just think, pick over all the different C values that C could be, what's the biggest that the n plus first derivative of that could even be? Let M be that number so we can see how bad this could be. And then the rest is just the rest of the error. Right? So yeah, recall that by all these letters here, there's a lot of letters here. By X, we're talking about the value at which we're approximating. A is the center of the expansion. And I just want to say that this is the formula that we'll be most focused on. It appears just slightly different in your book, but I think this is the one we should focus on. And this is the one that AP cares about too. So we're interested in that. So we'd like to return to our example from earlier and see how what the Lagrange error bound is for the one we were just doing, and see if our estimate fell inside of that. So here's the polynomial from earlier. If you remember us doing this, and that's the answer I wrote down on the board from my calculator. You did the same. So I just want to recall that that's true. So in the previous theorem, let's see if we can apply this to the situation we're just in. The previous theorem guarantees that our error on the interval 0 to 0.2, say, I think that's an interval of interest to us, on that interval, that the error will be no greater than the thing we just saw in the last slide. That is m over n plus 1 factorial x minus a to the n plus 1. Now, let's just try to pick that apart. What estimation, what a polynomial did we use? We used P4. So here, n is 4. So that means we're using the next, this has the form of the next term, doesn't it? So down here we've got 5 factorial. Here we've got, here we've got x minus, well, we're doing 0, right? We're centered at 0, so a is 0. That's not too bad. So I hope you see where these things come from. 5 factorial. Why? Because we did P4, right? We did the 4th order. So the error will be, this will be a 4 plus 1 here. This power, same thing, 4 plus 1. 0.2, I hope you see where that comes from. That's the distance we are away from the center on the interval of interest where we're making this estimate. The center is 0, we said. Okay, now we still have some questions about where this 32 came from now. So that, we need to step off to the side and figure out why I wrote 32 here for the maximum value of the fifth derivative. So let's just make sure we're clear that by m equals 32, we mean this is the maximum value of the fifth derivative. Now, I've actually written down the fifth derivative, but it's not hard to get. The fifth derivative of e to the negative 2x, if this is our function, the fifth derivative you can see where this is going, right? The fifth derivative, in fact, you could write down a formula for the nth derivative for this one, couldn't you? Is 32, or excuse me, negative 32 e to the negative 2x. It's hard to read. Negative 32 e to the negative 2x, but there it is again, right? And what we're asking is, if we go back all the way to the very first slide I put up here, the form of the remainder will always be the next term, evaluate that next derivative, and the n plus first derivative. Evaluate at some value c. And what we're trying to capture here with this capital letter M is, like, how big could this function even be? Let c be the worst it could possibly be. We don't know what that value would be, so find just what the worst it could be is what we're doing. So, can you justify why the maximum of this function, the absolute value of the negative 32 e to the negative 2x, on this interval is 32. For this, we may actually need to either graph it, look at it in some cases, or use kind of extrema analysis that we've used from previous semesters, or just visualize it. This is not too hard to visualize. Right? What does the graph of negative 32 e to the negative 2x look like? Let's start piecemeal. What does the graph of e to the negative 2x look like? Sure, you do that. This is exponential decay, isn't it? Nice, beautiful exponential decay. Now keep in mind, actually the only part we care about is on the interval 0 to 0.2. So we've got this little interval. Looks like that, from 0 to 0.2. All right, well, wait, hold up. It's negative 32, but we're taking the absolute value, so maybe it still will look like that, right? We're looking for the absolute value of the maximum of the n plus first derivative. I want to make sure you hear all three of those things. We're looking for the maximum of the absolute value of the n plus first derivative. Right? That's what this is saying here, right? What is the absolute value of the fifth derivative here? So that's where we got the number 32. And does this provide an error bound for us? Yeah, you can go back and actually check the error we calculated earlier, and you'll see that we got an error that was inside of this amount. This is the biggest, for any value you want to use. If you're using this polynomial, instead of e to the negative 2x on the interval 0 to 0.2, you can be assured, friends, that wherever you are inside this interval, your error will never be greater than this. That's a good amount of confidence we have. Now, of course, again, we knew we were safe to begin with. We weren't very far away. Let's see if we can do at least one more here. I know the bell's about to ring, but I think that it'll be good for us to do this. So again, here we got a Taylor polynomial, second order Taylor polynomial, used to approximate this. We'll just tell you that that's what it is. You could come up with this yourself, taking derivatives, doing this from scratch, but we'll just tell you that that's the approximation for this. And we're on this interval. Said another way, we're on this interval, right? Negative 0.1 to 0.1, right? So how bad could this be? What's the, if you're using this instead of this for values of x between these two values, how bad are you ever going to be? So that's what we're about to figure out, right? So we've got to be really careful here. We said that that remainder on the second order, we'll call it here, is always less than or equal to capital M over, well, help me out here. We'll figure out what capital M is in a minute maybe, but let's figure out the rest of this here. Yeah, 3 factorial over The center happens to be 0 here again. So how far away will we ever be from the center here? It'll be 0.1. And in either direction, if we go in either direction, it'll be either negative 0.1 or 0.1, right? In this. But we're going to take the absolute value of that, so it'll just be 0.1 to the third. Now we just still need to figure out what the maximum error is of this. So maybe we do need to calculate the third derivative here. So we really need the third derivative here. We'd like to know what it is. Okay, it's not bad though. What is the first derivative? What's the second derivative? 1 plus x to the negative second, put a negative out front. And the third derivative is 2, 1 plus x to the negative third. Okay, so I think I'm good. Now we need to think about how this thing runs. What does this look like? For us, guys, this is now in some sense I can maybe just use my pre-calc knowledge. This is a rational function. How does this look? If you want to do like the first derivative test and think about the maximum of this function on the interval negative 1.1 to 0.1, you could. But how does this look? Let's see if we can get a graph of this. It's 2 over 1 plus x cubed. There's an asymptote that x equals negative 1, right? That's neither here nor there, though, because that's far away from where we are, right? And then now we just need to think, does this have kind of this shape or this shape? It actually doesn't matter because we're going to take the absolute value of it, too. We're going to... So what does that look like, the original function? So we're only on the interval negative 0.1 to 0.1 here. And on this interval, and actually, like I said, it actually ends up not mattering whether it's this way or this way, because we're going to take the absolute value of it. So so I think it'll look something like this. Only on the interval of interest. There's more to this function. There's more to this function, but that's the maximum. I mean, that's the... So where is the maximum for this function? How would you get it? If you plug in what? Yeah, it happens to be, it's nice, for the functions we've looked at today, the maximum value of the absolute value of the n plus first derivative happens to be at an endpoint. Could it be in the interior somewhere? It could. It often won't be. We just don't. But let me pull up. Let me graph this with you here. Oh, actually, I think I have it here too. But let me graph this and show you. So f of x is equal to what? We'll call it f of x, but you know that it's. Oh, did I have all this up here? All right, so this is not a huge surprise to us, but it looks like this. So there's negative 1 to 0.1, and we can just calculate f of negative 0.1 and see that it's 2.743 approximately.
You look in Spanish today. Yeah, exactly. Isn't this one? Yes.